Yeah, so for you're still there, right?
Yes, I'm here.
Yeah, so
Yes.
bias I had explained. Variance is like, I'll give you a diagram. Maybe I'll start the lecture itself. You see, you can see my screen, right? I mean, the example that is there on the screen, you can see it, correct? Hello?
Yes, I can see.
Yeah.
I can see.
Yeah, so you see, for example, you have created a point. I mean, your data set consists of x and y. So x is on the x axis, and y is the other values for the corresponding values of x. So that is the orange line, and suppose you fit y equal to x square to this particular curve. I mean, for this particular points, you get that as your decision in regression. So the first point is the orange line, which fits on all the data points. Just by if you get these values and take a standard deviation of this particular vector, then you would get a standard deviation value of 35.56 as shown at the bottom of the figure, and standard deviation of the gray line will give you a value of 34.17. Just from these 10 points, you can see that and standard deviation is just the square root of variance. So because of this reason, this is said to be a high variance system. Okay, is it clear now?
The question was how to define the variance actually.
Yeah, so variance is defined like you normally define variance. You take the mean of all the points, and then you take so x minus mu whole square, and you take the, so what you do is you take of this particular column of 0.01 to 105, you take a mean of that, and then you take a difference of that particular of the mean with each point, square them up and add them up. So that is how the variance is defined.
In layman terms, how we will say what is variance?
Variance is how much you deviate from the mean. If your mean is for example, a straight line will have zero variance, because for all the points the value and the mean and all the points will already be on the mean, right? So in that case the variance will be 0. So variance tells you how much how much you are deviating from the mean. That is the definition of variance. Okay.
Yes. Okay.
Okay, so I won't wait for others, because today's will be a quite intensive session on support vector machines. So there will be certain things. Support vector machines depend a lot on optimization, and optimization is out of scope. I mean, the basics of optimization are out of scope in this particular course. So I will try to give you an intuitive idea as to why everything works as it is. I mean, why everything is working in SVM basically, and you might have some problems in between. So you can stop me and ask me, and I'll try to give you a intuitive explanation of many things in between. Okay, so I'll start with the lecture. I won't wait for others.
So then will you start with the basics of it, SVM?
Yeah, I'll start from the I'll develop the SVM completely.
Okay. Thank you.
The derivation will be out of scope, because that is not possible to derive in this class. So I'll give you the basics of SVM only.
Exactly what we want here. Yes.
Okay, yeah. So the question that we are trying to answer in SVM is, suppose you have two classes. First of all, SVM can be used for both classification as well as for regression, but mostly it is used for classification, and therefore if you see, in most cases it is motivated from the classification setting. So support vector machines, so the question is, you have a set of points, a set of positive classes and a set of negative classes, and you have I have drawn 4 different decision boundaries. Now can somebody say which one is the best decision boundary among these 4?
This
Which is
fourth one,
is
last one.
Fourth one, right?
Yeah.
Yeah, can you say why?
Because there is a
is inducing less.
maximum margin from plus
It
and minus
it
classes.
is inducing less error and clearly classifying the positive and negatives.
Okay, why is the error for the fourth diagram less than the second diagram or the third diagram?
Because margin width is more.
Yeah, margin I understood. You said margin.
Actually, when we are doing the addition, when we are summing up all these things, positive and negatives, sigma values, we are getting the minimum value in the fourth diagram as compared to other diagrams.
Sigma means, what is sigma?
That is the summation of all these error terms, residuals.
No, error terms in this case means something on the left of your decision boundary. I mean, this is the decision boundary, the line. So anything to the left of your decision boundary is positive, and anything to the right of your decision boundary is negative. So as far as the classification is concerned, the second, third and the fourth will all have the similar classification. I mean, in that it will classify all of the points correctly. Only the first diagram will misclassify 2 examples. The other 3 will classify all of the points correctly. Is there any doubt in that, or is that clear?
It is clear. Okay.
Yeah, so then it is so if all of them are classified correctly, then there is no question of deciding on the decision boundary based on the error that you are incurring, because the error will be 0 in all the last 3 cases, second, third and fourth cases. So as somebody mentioned, the fourth diagram is the best, because the fourth decision boundary is the best because it is separating out the positive and the negative classes by a maximum margin. So what is this term margin? I will come to in a few slides. So basically what you can think of is maximum margin solution is most stable under perturbations of the inputs. So if the second and the third diagram, if you see, the margin, the line is passing very close to some of the training points, but those training points themselves may be spurious. They might have been there because of the noise, and because of that because of some training points you are changing your decision boundary, and therefore your method is not robust to noise, maybe in this case, in the second and the third case, which is why you want to separate out your positive and negative classes as far as possible, with the margin being sufficiently distant from both the classes. So that is your aim in support vector machines. And so before going to the formulation about how to formulate support vector machines, this is a small this is a I shouldn't say an idea, this is a small information that you need to have. Like there is a line or rather a hyperplane which is W transpose x plus b equal to 0, and it is an equation. This represents an equation of a hyperplane. So hyperplane in 2D would be a line, in 3D would be a plane of 2-dimensional plane, and so on. So the shape of the hyperplane doesn't matter to you right now. Just what matters is W is always perpendicular to this hyperplane. So W transpose x plus b equal to 0, if it's an equation of an hyperplane, then W will be perpendicular to this hyperplane. So how can you say that? So the proof goes as follows. Let us consider 2 points of this hyperplane, x1 and x2. Both of them are lying on the hyperplane, and W transpose x1 plus b equal to 0 and W transpose x2 plus b equal to 0, and W transpose x1 minus x2. So if you subtract these 2 equations, then it becomes W transpose x1 minus x2 equal to 0, which shows that W is perpendicular to the vector x1 minus x2, hence W is perpendicular to the hyperplane. Okay, so the first question is W transpose x1 minus x2 equal to 0. From there, how can we conclude that W is perpendicular to the vector x1 minus x2? Can somebody say?
theta will be 90 degree.
Yeah, so W transpose x1 minus x2 can be written in which form? I mean theta you get, there is no theta in that equation. So how do you get the theta?
Sir, these handouts will be available to us. I mean, we need not
This
write it.
Using
no,
the
this lectures I mean I upload the PDFs to some NPTEL web page. I hope they give you access to that. Okay.
No, it is not there.
somewhere we are, can we use with the okay, you address her question first.
Yeah, you can answer the question and then I'll come. Yeah, W transpose x1 minus x2 equal to 0. How can you break that up? They are vectors, okay? Yeah.
I think there is a angle between these two, no, perpendicular, and that's why we are taking the tan h and like this.
That is all fine. Suppose you have a vector x transpose y. How do you break that up in terms of, I mean, where is the angle coming up in that equation? That
The
is,
dot product of W transpose and x1 minus x2, both the vectors is 0. So the cos angle, when we do dot product, that's basically
yes,
magnitude of
yeah,
W transpose and x1 minus x2 transpose, means the scalar value of magnitude of these two vectors,
yeah,
and the cos theta. There
correct.
the cos theta comes, that equals to 0, so theta should be 90 degree.
Correct, correct. Yeah, that's the explanation that I was looking for. So W transpose x1 minus x2 can be, I think I have it somewhere also in this slide. So W transpose x1 minus x2 can be broken up as the norm of W into the norm of x1 minus x2 into the cos of the angle between W and x1 minus x2. And so W is non-zero in this case because otherwise it is a trivial thing. And x1 and x1 minus x2 will also be non-zero because they are two different points on the same hyperplane, and therefore the angle, the cos theta has to turn to 0, which is why we can say that theta is equal to 90 degree. So W being perpendicular to x1 minus x2 means that if you draw a line, you will see that x1 minus x2 is along that line. So W is therefore perpendicular to this hyperplane. So this is a small aside that you would require. I'll directly jump to the I'll directly jump to the formulation. Okay, so yeah, so one more thing is, somebody asked that whether these handouts are not available. So I suggest you to contact the NPTEL people because we are uploading them onto the drive. So they should give you access to that drive, or they should make it available to you.
Okay,
Okay,
okay, okay.
yeah. Okay, so this is the formulation. This diagram is a bit clumsy right now, but okay, so you have I hope you can see some negative points and some positive points on the left and some negative points on the right bottom. You are able to see, right? Or they are not, they are not being, it is not.
Yes, yes, we are able to
Okay,
see.
okay, fine. Okay, so if these are the points, then as I said, your aim is to find out this particular line which is not dotted, which is W transpose x plus b. If you can see my cursor, then I am where my cursor is moving, that is the line that you are trying to find out. So in order to find out, as I said, this is W transpose x plus b, and W is perpendicular. If you can see W, then W is perpendicular to this W transpose x plus b. Okay, so you have several points, and yeah, if you see that W, and I have also drawn x1, x2 and x2 minus x1 in order to show that W is perpendicular to x2 minus x1. Okay, so here there are 4 circled points. If you see, 2 on the positive side and 2 on the negative side, and these are called the support vectors. Although they are just points, they are said to be support vectors. This is way this has been, I mean, people have been naming this. These are the support vectors, the 4 points here, and W transpose x plus b is my decision boundary. So this is the decision boundary that we are out to find out, we have to find out. So our objective is find W and B such that the positive and negative examples are separated out as much as possible. So that is your aim. So how do I understand what is the positive, how much the positive and the negative examples are separated out? Yeah, how do I know how they are separated out? For that you define what is known as the margin. So how do you define the margin? You get the support vectors for the two classes and you take the distance between them. Distance along W, which is the W direction, you take the distance along that and you get the margin between the two support vectors. So this is the margin that you want to increase because you are out to find a maximum margin classifier. Okay, so
Why it is like that? Why we want maximum margin classifier?
yeah, if you see here in the fourth diagram is different from the second and the third diagram only because the margin is highest. Can you see that?
To clearly classify, right?
To clearly classify and to make your system robust. So that is why you preferred the fourth diagram as compared to the second and the third diagram.
Okay. So far so good. Okay.
Yeah, okay. So you want to maximize this margin. Till now it's fine that you just want to maximize your margin. So find W and B such that for any unknown sample, so let's say so you will think about the margin later. First let's think about how we will define the decision boundary. So you will define the decision boundary in a way that's given any unknown sample and given W and B, you have found, suppose somebody has come and told you that this is W and this is B for which you get the maximum margin. You just take an unknown sample, you do W transpose U plus B, and if it is greater than 0 we'll classify it as positive, else you will classify it as negative. This is the way you define your decision boundary, let's say. So that means that anything, so this is exactly analogous to what you have already done intuitively in the fourth diagram. So you take a point and and you do that W transpose X plus B less than 0, it will come to the left side. If you do W transpose X plus B greater than 0, it will come to the right side, and depending on the sign of that particular quantity you will define, you will classify it as one of the two classes. So that is exactly the same thing that you have already done. I have just put it in terms of an equation, that if W transpose U plus B is greater than 0 we'll classify it as positive, else we'll classify it as negative. So far so good. Yeah, so this is the thing that I was talking about. W transpose X is nothing but the 2 norm of W and the 2 norm of X into cos theta, which is the angle between W and X. Okay, so that is good. Okay, so the question is how to find W and B. That is the next question, because if that is done then we have effectively solved the problem completely. Okay, yes. So how to calculate W and B? In order to calculate W and B, obviously you need to depend on your training samples, because you have been given a large amount of training data and you will train your W and you will train the SVM classifier such that the accuracy or the accuracy on the training set increases, and so on. So it's not just like a normal machine learning problem. So you would depend on your training samples to find out W and B. So to calculate W and B, we need to look at the training samples, and we put two conditions. The first condition is, now this is the way SVM was designed in the first place, and therefore after this SVM has followed on from here. So what the condition that is being put here is, for all the positive samples, which means that all the positive samples on the top left, W transpose for all the points on the top left, W transpose X plus B must be greater than equal to plus 1. So that is the condition that you are putting, which means that all these points on the top left, when you do W transpose with those points and you add B to them, you will get, you need to have the value of that W transpose X plus B must be greater than plus 1. That is the first condition that you are putting. And the second condition is, for all the negative samples, that is all samples which are on the bottom right, you need to find W and B such that W transpose X minus plus B is less than equal to minus 1. Okay, which means that so these are basically these two equations, which is W transpose X plus B greater than 1 and W transpose X minus plus B is less than minus 1. Okay, so we have two constraints. So these are called constraints in an optimization problem. In an optimization parlance, these are commonly known as constraints, and there is a very simple way in which we can combine these two constraints. How? We define another variable yi such that yi equal to +1 for positive samples and -1 for negative samples. So basically they are just the classes, +1 -1 you put, and you get the variables yi. Now we can combine these two constraints in this one equation. Yi into w transpose xi plus b is greater than equal to 1. How we combine these two constraints to this one constraint is clear, right? Or should I detail it a bit more?
Please detail it.
Not clear. Yeah.
Okay, so okay, I'll ask you, one of you, to go along with me here. So w transpose x plus b, the first equation which I am circling right now, what is the yi for this particular example? Can somebody say?
Positive.
Yes,
Positive 1.
positive 1. Okay, and what is the yi for the next equation?
Negative 1.
So if you multiply yi to both the equations, so first equation anyway you are multiplying by 1, so I don't care about it. The second equation you are multiplying by yi. How does the equation change? The left side becomes yi into w transpose x minus plus b. How does this side change? The right hand side of the inequality?
It will become positive. No?
It will become positive, and the inequality will
Greater than, it will change.
Yeah, so basically if you multiply yi with both of these equations, you are basically getting the same equation, same inequality. Am I correct?
Okay.
So that is why, so am I clear, or is everybody clear with this, or are there any doubts?
Yeah, clear.
Yeah, so which is why you can combine these two constraints with this variable yi to get a single equation for these two constraints. Okay, and the other thing which you require is, okay, so all of these negative samples will be less than -1, all of these positive samples will be greater than +1. You say that these support vectors will be exactly equal to +1 and -1. That is another constraint that you put. I mean, that is not basically a constraint. All of them greater than +1 and all of them less than -1, the closest points, you set them to be equal to +1. Okay, so for the support vectors, wi into w transpose xi plus b is equal to 1. That is how you set up this optimization problem. Okay, so now we come back to the actual motivation of our problem of support vector machines, which is what? All we wanted was to maximize the margin. All we wanted was to maximize the distance between the two support vectors between the support vectors of the two classes. So in order to maximize this margin, we need to compute the margin first, and then only we can maximize it, correct? So how to compute this margin? Okay, so you can see this big x plus and big x minus points. These 2 points, can you see this two big x plus and x minus points that I have drawn? Are they visible?
Yes.
Yeah.
Yes.
Okay, so from the origin you draw a vector. So this is basically the vector towards x plus and the vector towards x minus, and the line join and the vector joining x minus to x plus would be x plus minus x minus, which I have drawn here. So this is x plus minus x minus, and this is exactly your margin. I mean, this is your margin in the sense that this is a vector which is along that you can understand this like this is a vector that is probably giving you some sense of the margin. This is exactly not the margin, because margin would be the perpendicular distance between these two lines. So this is giving you some sense of the margin. Now I have introduced the vector w, I have introduced the vector x plus minus x minus, and I have now you want to find out the perpendicular distance between these two lines. Now can somebody tell me among these two vectors, which one is perpendicular to these three lines in this case? There is
W,
one
W, no?
Correct, yes. So you so W is the vector which is perpendicular to all these lines. So therefore, in order to find out the perpendicular distance between the two lines, or in effect in order to find out the margin between margin in this case, you will need to project this x plus minus x minus vector, which is this particular vector, that the vector between the two support vectors. You need to project it onto W. Is it clear? Okay. So when you project it onto W, so what should be the magnitude of W? This is a very what should I say?
We want maximum, no? Margin should be maximum.
Again, your margin is not W, correct? Your margin is this x plus minus x minus, which is projected onto W. So
approximate, no?
Yeah, so it is you have to project it onto W, right? So when you are projecting it onto W, what should be the magnitude of W in order to get the sense of, so see, basically what you need to do is you need to maximize the margin if you want to maximize the length of the vector x plus minus x minus. This much is clear, right?
Yes.
So when you project it on W, what should after projecting on W, if W itself changes the magnitude of x plus minus x minus, then you have in effect lost the actual information that was there. Is this point clear?
Yes.
This point,
W is greater than x plus minus x minus, right?
No, W is not greater, W is not lesser. You can't talk about W itself. So what I am trying to say is, let's say you are trying to project on a vector in order to find out the how can I say, yeah, so you are trying to project this x plus minus x minus vector. So let me call this the vector z. So so you are trying to project this vector z, and you are trying to find out the length of the vector along the direction which is perpendicular to these three lines, which is given by W. So all you require from W is the direction. You don't require the magnitude of W, because if you use the magnitude of W, then once you project Z onto W, then the magnitude of Z again will change. Am I correct?
Okay.
So see, this the projection is nothing but this W transpose X. Okay, so basically what you will do is you will do W transpose Z in this case. So if you do W transpose Z, and if W itself has a magnitude, then your projection magnitude will also change, correct? Am I clear, or are there doubts in this? I sense there are some doubts in this.
Could you repeat the last sentence again?
Yeah, so in this equation, W is there, X you replace by Z. Z is nothing but x plus minus x minus. Okay, I am calling that as Z. So you want to find out the projection of Z onto W, which means that you have to do this particular operation, which is W transpose X or W transpose Z. W transpose Z, as somebody said, and the formula is, it is the norm of W into the norm of Z into the cosine of the angle between W and Z. So if the projection, so if you are trying to, so and then what you will do is you will try to maximize this margin, you will try to maximize this W transpose Z. So if you try, if you are trying to maximize this margin and W itself has some magnitude here, then you might maximize this margin without changing Z at all. You might as well make W infinity, and then this margin will become infinity, but Z might be very small in that case. Am I correct?
Yes.
So W cannot have a magnitude in this particular case. W's magnitude has to be 1, because unless W's magnitude is 1, then this particular projection or this particular margin you can increase without actually increasing the margin. I hope it is clear now. If you have any doubts, you can stop and ask me again, because this is one thing that you need to understand. After this will just be normal algebra. Okay, so since I hope everything is clear to everybody. So the question is, so the answer to this is project the distance between x plus and x minus on the vector W. So so this is the question that I asked, should W be normalized? And your answer is yes, W should be normalized. Normalization means you take W and divide it by the norm of W. In that case, this will become a norm of 1. The norm of W will become 1 in that case. So the vector joining x minus and x plus is,
Sorry to interrupt,
yeah,
Soumya.
yeah.
Normalization means we are calculating the Z score here, na? Normalization, what you are doing actually in normalization process?
Normalization means, see, can you see the bottom of my screen where I have written check?
Yes.
So if there is 1 2 is your vector, you take the norm of it. So the norm of 1 2 will be 1 square plus 2 square, which is root over 5. This term, what you are seeing on the left, 1 2 by norm of 1 2, there should be another norm here, norm sign. 1 2 by the norm of 1 2, that is precisely known as normalization. Okay. So 1 2 by the norm of 1 2, if you do it, then the vector would be 1 by root 5 and 2 by root 5. So what is the 2 norm of this particular vector?
It's around 1.
It's not around, it's exactly 1. Okay. So so that is what you want. You want W to be of norm 1. This is what I was trying to mention in the previous slide also. So basically your projection should be onto the direction of W, but W should be of norm 1. So basically that is what you are doing it. You are doing W by the norm of W, and you are projecting x plus minus x minus onto W onto W. So W transpose into x plus minus x minus. So if you see from the previous slide, W transpose x plus is equal to 1 minus B, and W transpose x minus is equal to minus 1 minus B on the support. I am talking about the support vectors now. So W transpose x plus is 1 minus B, and W transpose x minus is minus 1 minus B. You take you do this and you get 2 by norm of W. So basically the margin becomes the 2 by norm of W. Is this clear? This margin is nothing but 2 by norm of W.
So far so good.
Correct. So thus the problem becomes maximization of 2 by norm of W, because you want to maximize your margin and this is the margin value. So maximization of 2 by norm of W, and these were your constraints, that is Wi into W transpose xi plus B is greater than 1. This constraint, I mean this particular problem, is a bit difficult to handle in optimization, and so this can ideally be just an equivalent formulation of this particular thing can be, if you are maximizing 1 by norm of W, you may as well minimize norm of W square, and anything if you are minimizing, where you can put a square, I mean norm, because norm is anyway it's a root over term. So you just take a square of it and you will try to minimize the norm of W, subject, and the constraints remain as it is, subject to yi of W transpose xi plus B greater than 1. So this is a quadratic optimization problem. Why? Because the objective function is quadratic in nature and the constraints are all linear, and therefore from optimization we know that this is this has to have a unique minimum. So there is so SVMs will have a unique solution in this case. Okay, now unfortunately, as with all machine learning problems, there is a trade-off in support vector machines also, like as we saw in the first slide itself. But there may be cases where the support vector machines will run into more, I mean trade-offs which will be not easier to see by in clear eye. So okay, somebody is again joining now. Okay, so here there are some positive negative examples. So I have done 3 decision boundaries here. Okay, there are 3 decision boundaries. So the first decision boundary has the first decision boundary means the decision boundary which is on the top, or rather the rightmost decision boundary, which is not doing where my arrow is, which is not doing any classification error. All of them are classified correctly. The middle one has 1 classification error and the leftmost one has 2 classification errors. So always there will be a trade-off between margin and number of mistakes on the training data, because your training data in most cases won't be so good that you by a single margin you would be able to classify all of them correctly. That won't happen in most cases. So trade-off between the margin and the number of mistakes in the training data. You see that the first which is making 2 mistakes, that has the highest margin, because the positive and the negative classes are separated out, because the positive and the negative classes are separated out by the maximum point, by a maximum distance, but the others are, the margin is going on reducing, but the classification error is going on classification error is also going on reducing, which means that there is a trade-off between the margin and the number of mistakes on the training data. So the root of this problem is, I had given a problem to the optimization software to say that all positive samples have to be greater than 1, which means that W transpose X plus in W transpose X plus B, all of them had to be greater than 1 for all samples, and this might be a difficult problem for the optimization software to solve. Similarly, all negative points W transpose X minus plus B less than equal to minus 1, also it may be too difficult. First of all, it might be too difficult, and also it might lead to greater it might lead to overfitting. So this is the modification that I will do. Okay, so I'll not talk about equations now, equations will come later. This, just understand this from a geometric point of view. So this is the same diagram that was there before. I have now added, and the support vectors are also similar, like there are 2 positives and 2 negatives. Can you see point number 1 and point number 2, the 2 negatives point which are actually with to the left of the support vector? These 2 points.
Yes, one is misclassified and one is,
yeah, one is misclassified, which is this, the point 2, and the other is known as margin violation, because it is within the margin. I mean, basically there should have been no points within this. So if you consider this to be a street, this particular these dotted lines, if you consider this to be a street, there should be no dots within this particular street, no positive points, no negative points. But if you are getting a positive point, that means you are violating your margin, but at the same time you are classifying this correctly, because this is still to the bottom of this particular decision boundary. However, this particular point which is marked by 2, this is to the other side of the margin, and therefore you are misclassifying the point completely. This diagram is clear, right?
yes, but when it is violating the margin, is it inducing some error in the judge or accuracy?
Yeah, I'll come to that. That will come in the formulation stage. I'm just talking about that there can be situation, I mean you can probably want this situation also. This is a situation that is not very bad. If you see that this negative point which is 2, if you try to classify this correctly, then it will overfit like anything. I mean, you won't be able to do a very simple classification just because of 1 point. You need not change your classifier. So that is the main point that you need to understand from here, that this is not a very bad situation. This is a situation that you might want in certain cases when you have a large number of points. Okay, so yeah, so what you do is I allow some positive samples to satisfy W transpose X plus B greater than 1. This was my original formulation, but I allow some positive samples to satisfy W transpose X plus B greater than 1 minus some positive quantity. What does this mean in this diagram? It just means that initially I had asked all my positive samples to move to the left of this particular support vector, or this particular line. I had asked all of them to be above this line or to the top left of this line, whatever. Now I am allowing some points to be below this line. How below, that I don't know, but I allow some of the positive points to come below this line also. Similarly, I allow some of the negative points to go above this line, to go above this particular W transpose X plus B equal to minus 1 line. So for that I change the constraint which was initially W transpose X minus plus B less than minus 1. I change that to minus 1 plus a positive quantity. This is clear, right? Are there any doubts in this? I hope
No,
people.
so far so good.
Yeah, others, no doubts, right? I don't think others are listening also. Anyway, okay, so W transpose X minus plus B is yeah, so you are subtracting a positive quantity for the positive example and you are adding a positive quantity for the negative examples. And okay, yeah, so these positive quantities which I talked about in the last slide, they are known as slack variables in optimization and they are denoted by psi I or xi I. So W transpose xi, okay, there should be a plus here, W transpose X plus B greater than equal to 1 minus xi plus, and W transpose X minus plus B is less than equal to 1 minus 1 plus xi minus. Similarly, as I showed in the previous, and I mean when I was formulating SVM for the first time, if I multiply if I multiply by y plus and y minus, I get y plus into W transpose. So basically, you are just multiplying this by plus 1 and multiplying the second equation by minus 1, and therefore these two equations again become similar. So thus the constraints become yi into W transpose xi plus b greater than 1 minus xi I, and xi I is greater than 0. Is this clear?
Is I and how this new term is coming into the picture?
Yeah, so you understood I wanted to have a positive quantity here, right?
Yes.
So this positive quantity I am denoting by xi I. That's it.
Okay. Which you are allowing to violate the margin.
Yeah, I am allowing some examples to violate the margin.
And that that term that is called, you are adding as a xi I in this
Yeah,
equation,
yeah.
right?
So they are known as a slack variables and they are known as xi I. I am denoting them by xi I.
Okay.
Okay. So the SVM problem now becomes minimization of W, which is the original problem. So minimization of the norm of W square such that yi into W transpose xi plus b greater than 1 minus xi I and xi I greater than 0. This is the formulation, I mean the objective remains the same, just that the constraints have changed. Now what is the problem with this formulation? The problem is, let's say I make xi I equal to infinity. I make xi I, in all the xi i's go to infinity, which means that xi I greater than 0 is satisfied. That constraint is not stopping you from making xi I equal to infinity, positive infinity. And you make W go to 0, which means that minimization of W is, I mean norm of W square cannot go less than 0. So you have achieved the minimum value of W. So W goes to 0, and if you see here, then the yi, which is just plus 1 or minus 1, W transpose xi, so W transpose xi also this also becomes 0 because W has gone to 0. You have some constant b, you don't know what b is, and you have greater than minus infinity. Okay, so whatever, hello,
Are you going to penalize this now?
yeah, so that is what I am saying. So the objective needs to penalize the growth of xi I.
Okay.
Is the motivation clear that why I need to put xi I there? Because otherwise xi I can happily go to infinity, all my constraints are satisfied, this can minimize, this can go to minimum value of 0 and nothing is there. So basically W is 0, B is, I don't know what B will be, W is 0, so that's gone. So is it
How the optimization is playing the role here?
yeah, so see, xi I can be greater than 0, right? So minimization of W square, what is the minimum value of norm of W square?
Value of W square is 1. So
No, minimum value of, I mean what is the minimum value that you can achieve for,
infinity we are
what is the minimum value of norm of W square that you can achieve?
Excuse me, sir.
Yeah,
I didn't get this. When xi tends towards infinity, how W norm tends towards 0?
no, I am saying that what is, okay, let's look at this in this way. What is the minimum value of W that you can achieve? W norm of W square that you can achieve?
1.
Why 1? Why can it not be 0?
It can't be 0 because there are certain support vectors we are adding.
Okay, So for the support vectors, what are these particular equations?
It is greater than and less than 1, na? Greater than equal to 1.
Greater than equal to 1, but this xi is there, correct?
Yes.
So you can make xi equal to infinity and still this equation will hold, right?
Right.
If the right hand side becomes minus infinity, then whatever you do to the left hand side, it doesn't matter. So basically your problem becomes very loose in this sense. So this is what is known as the optimization problem becoming very loose. So you have introduced a variable, and with that variable you are not so you can get a trivial solution from there from your problem, because you are not penalizing that particular variable that you want.
Right.
One more motivation as to why this xi should be penalized is this C. Finally, this xi is basically an indication of how many examples are violating my margin. Okay. So while training your support vector machines, if you don't penalize the examples that are violating your margin, then all of your examples will violate the margin and you will still be happy. But effectively, in essence, you have got nothing.
But it will make no sense.
It will make no sense, correct. So that is why you need to penalize this xi. Am I clear now? Is everybody clear
Yes.
with this?
Yes.
Okay. So finally we come to the support vector machine formulation. This is the final formulation that is there in support vector machines. I mean, in most cases, not in most cases, in all cases, this is the formulation that will be solved, that you minimize w comma xi. Now you see earlier it was just minimization. I had put a w here, just a w was here. Now I am putting w and xi with w. And this was already there, norm of w squared, this is the margin. So I am trying to minimize the norm of w square, which means I am trying to maximize the margin, and also I am trying to minimize some constant c with the summation of xi. Xi is summed up over the n examples. So what this means is you cannot go on increasing xi and still be happy. Your xi have you can only increase. So this optimization problem brings in a balance between the norm of w square and the summation of xi's, and that balance is defined by the constant c, and the constraints are as it is. So what are the possible values of c? First is c becomes very small. If c becomes very small, then this optimization problem, I mean, you think of this in an intuitive way, like if c is small and I am trying to minimize this sum, then I can increase xi if I want, because c is small. So xi can still increase, and this optimization problem will even then it will be low. I mean, the value of this objective function will still be low. So xi can increase. If xi can increase, this means a large margin is there, but there will be many misclassifications. C is large, which means that I am increasing C to be very high. If C is very high, then xi cannot increase, because then even a small increase in xi will increase this objective function, and I want to minimize this objective function. So xi cannot increase, which means small margin. And c equal to infinity, which means none of the xi's can be positive, and hence all of them have to be 0, which is the original formulation that you have in the SVM. That is known as the hard margin formulation of SVM. Okay, I hope. Yeah, any questions?
Many times I heard that in SVM there are it is very difficult to decide the hyperplanes and to select the different kind of hyperplanes or kernels. Is the concept of kernel is there also?
Yeah,
Could you elaborate?
yeah, kernels I will come. I mean, kernels of course I won't be able to describe, because for going to the kernel formulation you will require extensive optimization. So I'll discuss about kernels in a bit. Till this much is clear, right?
Yes, so far so good.
Okay. So yeah, so here only kernels will come. So the first thing is see, xi is greater than 1 minus wi. So from this equation, yi into w transpose xi plus b greater than 1 minus xi. From this equation you can get xi, you can put xi onto the left side. So xi becomes greater than 1 minus wi into w transpose xi plus b, which is this equation, and xi is greater than 0 was already there. So basically how you can define xi is the maximum of 0 and 1 minus wi yi into f of xi, where f of xi is w transpose xi plus b. Hence the final problem becomes minimization of w, which is norm of w square plus c and the summation over 1 to n, and I have just replaced xi by this particular term. Is this clear? Again it becomes a variable just of w. Xi is again.
Could you please elaborate the last two slides? These last two slides.
Yeah. So you got up till this, right? Till here it's clear.
Yes, it is clear.
So you put xi onto the left hand side and put greater, and xi becomes greater than 1 minus yi into w transpose xi plus b, correct? Which is this equation.
Okay.
And xi was already greater than 0, that is your another constraint. Xi is greater than 0. So you combine these two constraints, so which means that xi is the maximum value of 0 and 1 minus yi into w transpose xi plus b. This is how we can combine these two constraints, because xi has to be greater than 0 and xi has to be greater than 1 minus yi into w transpose xi plus b. So whatever the maximum of these two, xi I am taking that to be the maximum, I am taking that to be the value of xi. Okay. So yeah. So and therefore what becomes is I am trying to maximize and then here in the formulation I am just replacing xi by this particular formula, which is maximum of 0 of 1 minus yi into f of xi. This is the formula that I want for w. Okay. So this is known as the primal SVM problem. This is known as a primal SVM problem. Why primal? Because all you wanted was to find out the value of w, which is what you started with. This can be converted to an equivalent dual problem, and this from here to here, from these two sentences, there are considerable optimization exercises involved. I am not going into that because they are out of scope. So this, I mean, just believe me that this particular problem which you see up top can actually be converted into this particular problem. There are some alpha constants. Now your whatever was there in minimization becomes a maximization problem. That is a standard thing between primal dual problems, and you get some alpha I greater than 0. These are yeah, I will not go into the details of this, but these are some constants which are lying between 0 and c, and you have some more constraints of alpha I into yi equal to 0, and you have this big optimization problem now. So these two problems are equivalent, so you can solve any one of them and you will get the same answer. Okay, so that is the dual formulation of SVM. Okay, now note one important thing. In the primal formulation of SVM, which is the top one where the minimization was over w, there you had minimization over w square, and x was involved in w transpose xi plus b. I mean, x is your training sample, so xi was involved in w transpose xi plus b. Am I making sense? Correct? I mean, is everybody clear? Is everybody seeing this?
Yes.
The only way where xi is involved in your optimization problem is w transpose xi plus b. That is the only place where xi is playing a role. Here if you see in the dual problem, xi is playing a role only in the form of xj transpose xk. Is this visible? Is this clear?
No.
You can see this problem, right? I mean, the formulation which I am circling right now.
Yes. Yes.
So here if you see, the first term is alpha I, which is a constant, which is your decision variable, not a constant, which is a decision variable. Then you have alpha j, alpha k, yj, yk. Xj is just multiplied with xk. Xj is not multiplied with any other weights or something. Is this clear?
Actually, can you summarize in common in the layman term here?
Okay, note that in the dual case, I mean, see, the first thing which you need to understand here is consider 2 points, x1 and x2, let's say. Okay, in this primal solution you will have W transpose x1 in one of the terms and W transpose x2 in another term, correct?
Okay.
In the dual form you will not have x1 and x2 separate from each other, you will only have them in this form. You will have x1 transpose x1, x1 transpose x2, x2 transpose x1 and x2 transpose x2, correct?
Yes.
That is the only point that I am making here. That note, in the dual formulation the training samples xj xk appear only in xj transpose xk form. They are not appearing in any other form in this formulation. That is the only thing that you need to know. And we will come to why this is such an important, why this is a very big advantage. This is the reason why kernels are so important in SVM. That in this particular form, if you need, I mean in the primal form, if you needed x1, you needed to have W transpose x1 computation. In the dual form, if you need to solve the dual form, then all you need to do is take x1 transpose x2, x1 transpose x3, x2 transpose x1, x1 transpose x2, whatever. All the training samples will appear only in dot product format. Is this clear?
Yes.
Okay. So let's look at this particular classification problem. So you have a series of positive classes and negative positive examples and negative examples, and as you can see they are very easily separable by means of a circle. Okay, but in this particular case, how I mean whatever I have presented till now, this SVM won't be able to solve this problem, because there is no, these two classes cannot be linearly classified. So there will be a huge amount of training error if you train a SVM, linear SVM on this. So does SVM fail in this case? Now SVM was a very powerful tool. It was the most powerful tool before the advent of neural networks. So SVM cannot, obviously people found out a way to make SVMs work for this as well. Now this is the trick, and this goes on and this comes up as the kernel trick much later. So what you can do is, now this trick is very elegant in the sense that you have x1 x2, you convert this to polar coordinates. So your x1 x2 becomes r theta. So x1 x2 was like this, r theta is like this, because r below a particular threshold comes to the left, r above a particular threshold comes to the right. And now you train a SVM is able to separate out the two. Is this clear? Is the intuition clear behind?
Yes. Yes.
Okay.
How we are going to classify this?
Yes. So this is one simple case where you are just converting x1 x2 to r theta, where the coordinate dimension is not changing. Basically you are taking x1 x2 and you are putting it, the 2D coordinate you are the Cartesian coordinates you are converting to the polar coordinates. That's all what you are doing. Sometimes your data will become linearly separable if you go to higher dimensions. Let's say you consider this particular example, you want to classify the squares from the circles, they are not linearly separable in the left hand diagram. What you do is you append, this is just the x axis that you have, you append y equal, you take a square of all these points and you append that, so it becomes a 2D point. So now it has one of the dimensions have increased. So earlier, let's say this is -1, so this point in this case becomes -1, 1. Okay, this point becomes -1, 1, this point becomes 1, 1. And similarly you do it for, you take the square of all these squares, square points, and now it becomes linearly separable. Is this intuition clear?
How you did it? I don't get it.
How I did it means, is the intuition clear that whenever I am adding one dimension, sometimes the data becomes linearly separable?
Separating squares from circles, and circles you are taking into consideration within a marginable range.
Yeah, so I have to separate out the squares from the circles, This was not possible in the left hand diagram. That part is clear, right? From a
Yes,
linear
yes.
classifier, that is not possible.
Not possible.
So what I do is I take a square of all these points. I mean, I've just created this example. It's not like somebody found this out. I'm just creating this example saying that okay, it was all on the x-axis. Now I'm appending the y-axis to it. And how do I decide on the y values? I decide on the y values by taking a square of all these points. So this is probably -1, this particular circle which I'm pointing to right now. So this becomes -1, 1. This is probably -2, this becomes -2, 4. This is -3, this becomes -3, 9. Correct? You got it?
Yes, yes.
And after that it just becomes a linear classifier on the right.
Just by squaring your problem is solved.
Yeah. So just by squaring means I am squaring and going on to a higher dimension. So it's not like the squaring that is of importance here, it's the higher dimension that is important. So I'm going up to, yeah.
In other terms, we can say we are enlarging the values, right?
Not exactly enlarging the values. You are, let's say, how can I say? So basically, the points were the points were not discriminative on the x-axis. You are, I mean, not discriminative means they were not discriminative by a linear line on x-axis. So what you are trying to do, you are trying to separate them out by adding another dimension to that particular point. And you are trying to see whether adding that dimension is linearly, you are able to linearly separate them. Okay.
Fine.
So sir, this is for any order of magnitude, right? So if it is for two order of magnitude, two dimensions are there, for example, in a particular case, and we are trying to plot it on a plane, all the points, and we are not able to segregate it because they are overlapping, or we are not able to figure out a kind of a cutting plane. We are not able to figure out, right? So what we will do is we will introduce another dimension, which will help us to align those parameters in such a way that in a 3 dimension
it will become separable.
Is possible.
Yes.
But to change a 2D plane into 3D plane, we have to do certain things. Like we have to either square it, or we have to either make it a power of 3 to make it plotted on that 3 dimension, because we have to figure out some point on the 3rd dimension also where these will be mapped.
Correct. Yes. Precisely. So, yeah, what you are saying is correct. So if it is not happening in the 2D plane, you might go to the 3D plane. Even if it is not happening in the 3D plane, you might go into the 4D plane. Finally, you might go on to the infinite dimensional space also. Right. So your intuition is correct. So let's say, just as you said just now, that let's say I have a case when x1, x2 can be separated out. x1, x2 was initially not separable in the R2 space. But in R3 space, if I convert x1, x2 into this form, that like x1, the first coordinate in the R3 plane becomes x1 square, the second one becomes x2 square, and the third one becomes √2 times x1, x2. If you are doing this manipulation, like you see, this manipulation which I showed just now is exactly something like this. Like if you take x1, if you have just x1, and if you convert it to x1 and the second coordinate you make it as x1 square, that is what I have done here. So similarly, if you took x1, x2 and did this sort of a thing, then probably your problem becomes separable. You don't know whether your problem will become separable even in this space or not, but you can at least try that whether it becomes separable in this space or not.
Sir, one question here.
Yeah.
Could it be like we would have done x cube instead of x square, or is it a set formula that from 1 dimension to 2 dimension?
No, you can do it in different formula, in different ways also, but then for different ways the kernel trick won't help you in all cases. So that is why there are some very specific kernels which are there, and so finally the kernel trick is such an elegant trick that you don't need to think about all these things. You don't need to think about what the first coordinate in the enlarged space would be, what the second coordinate in the enlarged space would be, and that is precisely where kernel trick comes into play. Okay, so I'm just giving you an example here. This is not how you will do it finally. I will show you how you will do it.
Okay.
Okay, so let's say your x1 and x2 was there and you want to go to the 3D plane and you want to go 3D space and you want to do it in this way, like x1 becomes x1 square, the second coordinate becomes x2 square, and the third coordinate becomes root 2 times x1 x2. And your primal formulation, as you saw, is here, which is minimization of w belongs to RT and w square, norm of w square plus c of max, whatever term was there before. So how you need to do is, you need to have this x, you need to get all this training samples, and you need to give this particular transformation to all these training samples, and then you solve for w. So w in higher dimensional, so w becomes higher dimensional space in this case, because now you are operating in a 3D plane, your w will also be 3-dimensional. Is this clear?
Of course, sir. Yeah,
Yeah.
that's good.
Yeah. So now the problem is, if the space where I am moving to, if d is much greater than d, which is the
Something
original.
your voice is breaking actually.
Hello?
Your voice is breaking.
It is clear, Sandeep sir.
Okay, so it is
Yeah.
might be problem from my side.
Might be a
Thank
problem.
you. Thank you. Thank you.
Yeah, so the problem is, if capital D, which is the new dimension that I am having, if it is much greater than the original dimension, so in this case it is just 3 and 2, so it doesn't matter. So let's say this is R100 and this is R2. So if 100 is much greater than 2, so you have 50 times more parameters to estimate in the primal problem, because you are estimating w, which is directly proportional, the number of the dimension of w is r of capital D, and therefore we need to avoid this. So this is where the dual formulation as well as the kernel trick comes into play. So let's look at the dual formulation again, which is max of alpha I greater than 0, which is this big formulation which I did not derive. You see xj transpose xk, the only difference with the primal part was, in primal wi transpose xi was there, here only xj transpose xk is there. Xj is not being combined with any other terms in this entire formulation. So you can as well as do what, you can convert xj into the higher dimensional space by means of this phi of xj, and you can convert this xk to this higher dimensional space phi of xk and do this dot product. So what is the big, I mean, why are you even saying this? We are still doing the same thing. The first, I mean, we will not do the same thing finally. So the first problem that we have subverted is, you see alpha, this here the problem is over alpha I. Alpha I is dependent on the number of training samples. So here the number of depending on the dimension of xj, I don't need to change the number of variables that I am solving for. Is this clear in the dual formulation?
Yeah, it's still same, right?
No, it's not same, right? You see here in the primal formulation, w had a dimension of rd, which is the dimension where you have projected your x1 x2 to, or
Right.
points to. So depending on whether you project to a 100-dimensional space or a 1000-dimensional space, the number of variables that you need to solve for will change, correct? In the dual formulation, it is alpha I goes from 1 to n, which is the number of training samples. So irrespective of wherever you go to, the number of variables that you solve for always remains the same.
Okay. Okay.
It is always n, it is equal to the number of training samples. Now
It's just that their dimensions have changed.
yeah, exactly. Even if the dimensions have changed, you are not solving for greater number of variables.
Okay. Sir, one question here, actually just curious to know.
Yeah.
See, if I'm trying to solve this problem
Yeah.
for a 2D plane,
Yeah.
I moved into 3D plane,
Yeah.
right? And in 3D plane also I'm not able to segregate them properly.
Yeah. Then
I
you
had
will
one
need to
dimension.
then you will need to move to higher dimensions. Yes.
Yeah. And this machine learning algorithm
Yeah.
does that also, like supports that also, like you can go to higher magnitude to any number.
Yeah, I will
Till
show
the time
that.
you are able to segregate them properly.
We can go up to infinity. basically.
Oh, okay. Okay.
Okay, so
Okay.
now the kernel trick comes into play. So the first advantage was the number of variables which you were solving are not dependent on the space where you are projecting your xi and xj2. That's the first advantage that you are getting from the dual solution. The other advantage is, you see, the why I am focusing continuously on this particular way, where it is way in which the training samples are occurring, which is phi of xj transpose into phi of xk. So kernel is defined as like this. So kernel is k of xj comma xi equal to phi of xj transpose phi of xi. This is the definition of kernel. There are more I think one more condition to this, but which means that it should be positive definite, but I leave that for now. So this is the definition of kernel. Let's consider this as the definition of kernel, which is k of xj comma xi equal to phi of xj transpose into phi of xi. And now you do the same thing, which is x1 x2, which is x1 square x2 square root 2 of x1 x2, which is what I started with. This is what I started with.
Right.
And let me try to find, why is this happening? Oh, just a minute, I think my system is hanging. Okay, okay, yeah, phi of x1 to x2 becomes, so x1 x2 becomes x1 square x2 square root 2 x1 x2. And now I take this, I do this computation, which is phi of xj transpose phi of xk. I do that with x and z. So phi of phi of x transpose phi of z becomes x1 square, becomes a dot product of x1 square x2 square root 2 x1 x2 and z1 square z2 square and root 2 of z1 z2, which if you break it up becomes x1 square z1 square plus x2 z2 square plus 2 of x1 z1 x2 z2. What is this term that you have got in the bottom? I hope it's visible, but hello?
Sir,
Yeah,
not able to term it, but I'm
It
able
is
to
not.
understand.
it is
It
x1
is
square z1 square plus x2 square z2 square plus 2 times x1 z1 into x2 z2. Can you write it in any short format, in any?
x1 x1 z1
Yes,
plus x2
A plus
z2
B
bracket
square,
square
correct. So
square.
it
B
is
plus
precisely this, right? x1 z1 plus x2 z2 square, correct?
Right.
What is x1 z1 plus x2 z2? It is nothing but x transpose z. Am I correct? This is correct, right? You are following me.
yeah,
Yes.
this
Yes.
is
So
reverse vector.
basically what you have done is, you have taken a dot product in the three-dimensional space. That's how you started.
Right.
You have taken a dot product in the three-dimensional space, which you can easily get from the two-dimensional space itself. You take this two-dimensional x, two-dimensional z, take a dot product in the two-dimensional space, get a square. You are effectively doing a dot product in the three-dimensional space.
Oh,
Okay,
okay.
is this fine?
Yes. Yes.
So so that is why I said that all those phi xi, phi x, all those things you don't need to worry. Kernel itself will take that into account. If you are just taking the two-dimensional x, two-dimensional z, taking a dot product and taking a square, you are effectively doing a dot product of this phi of x and phi of z. And that is where the kernel trick helps. You are doing something in the high dimensional space without even going into the high dimensional space.
Just by squaring it.
Just by squaring, I will show one more term which I mean, there you can do different. So this xt transpose z you can take to the power d basically.
Okay.
So to the power of d means you are going to the d dimensional space. Oh sorry, to the d plus 1 dimensional space. Okay.
So this happens because, like, you used on the previous slide. Can you go back to
Yeah,
previous slide?
yeah.
Because you use this x1 x2 mapping it to x1 square x2 square
No,
and
no,
root,
no, 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 no. This
right?
is not happening because of that. You may as well think of, I will take x and z, I will do x transpose z whole square and you will get something. Correct. You will get the value of whatever this phi of xj transpose phi of xk is there. You will do x transpose z, you will take a square and you will get this value. All you care about is this value. You don't care about how you got here. You take x transpose z, take a square and you will get this particular value. In essence, what I am trying to show or what people have shown is, when you are doing x transpose z whole square, in effect you are taking a dot product in the higher dimensional space.
Got it.
Okay. So without moving into the higher dimensional space, you are being able to compute the dot products in higher dimensional space. And mind you, this was only possible because I went to the dual formulation, because only in the dual formulation the xj and xk are related in this way. In the primal formulation there is still w transpose xj. So w transpose xj, there is no way of doing the kernel trick there. W transpose xj has to be done, like you have to convert xj to the high dimensional space and do a w transpose x there. You need to know this phi in that case. Now even without knowing the phi, you will be able to do something in the higher dimensional space. So we are doing a computation in the lower dimensional space, which is effectively doing a dot product in a much higher dimensional space implicitly. So this is implicit. This is not explicit in that sense, because you are not finding out the phi. All you are doing is x transpose z and taking a square or taking a d, because this you could write, because it was you are going from 2 to 3 dimensional. If I ask you to go from 2 to 5 dimensional or 2 to 6 dimensional, you won't be able to write also. But here you can just take x transpose z and take a part 6. You are actually doing something which is there in the 6 dimensional space. You got it?
Yeah.
So the most extreme case and the most famous kernel for SVM is the radial basis function, and if you know that this is exponential function, correct? So this is effectively, you can break this up into infinite number of terms, and this is basically doing a dot product in an infinite dimensional space. Okay. So this particular formulation is not possible, it is not possible for you to solve in the primal space. You can only solve it in the dual space. And okay, so this is known as a radial basis function, and this is the most widely used function, I mean kernel function for SVMs, where sigma is the only parameter. And okay, so with that, so with that I come to the end of the lecture on SVMs. Are there any doubts?
Awesome session. Very nicely explained.
Yeah, thank you. I'll have 3 more questions. They will be pretty simple, but I'll go through because NPTEL asked me to go through questions. So I have to go through. So are there any questions, or I can go through with the
Can you, Soumya, can you list down the just like Radial, we have the what kind of famous kernel? Can you list
I
down some more,
can
few more kernels?
I can, but I don't have it with me right now. I mean, I have not listed down in this lecture.
Fine.
So there will be polynomial kernels. Mostly there are polynomial kernels are there. RBF kernels are there. Polynomial kernels is the one which I talked about, like x transpose z to the power of d. There is one more variation to that, I think, 1 plus x transpose z to the power of d. Some that is also there. Then this RBF kernel is there. These 3 I remember. There are more kernels actually. I don't remember all of them. And kernels, you can combine 2 kernels and that again will be a kernel. So so there can be many kernel combinations also. Okay.
When you are combining, is it like a hybrid kind of thing, or
people don't combine generally, but in SVMs at least they don't combine. And but you just know that there are ways to make kernels from kernels. So basically, if you have one kernel, you can make other kernels from that. So there are certain rules about kernels which you follow. You can go from one kernel to another.
what is the need of that?
There is a need for that because you might want more complicated kernels. I mean, of course, that depends on that is a research question. So why you need different kernels? So that is a research question.
Okay, so we can go ahead with that research.
Yeah, sure.
Can you have one question?
Yeah.
Can you just brief explain me how the SVR algorithm is evolved using SVM?
SVR, if I go into SVR right now, it will be it will take more time. So SVR, actually I have not prepared for this, but because I thought that also in the lecture also I saw that it was mostly related to classification, and SVMs you will generally use only for classification. So if you want next lecture, I don't know whether I will find time, but if I find time I can give you a brief overview of how SVRs work.
Sure, sure.
I mean the main techniques will still be the same. The main technique, the main technique probably will, the main technique will still be the same, but there will be some small nuts and bolts which will be attached just to make it a regression problem. I'll give you a 5-10 minutes overview in the next lecture.
Okay, thank you.
Yeah. Okay. Okay. So
Sorry to interrupt. When it comes to bivariate problems, classification problem, it is absolutely fine. But when it comes to multivariate problem, then
I'll give you I'll give the one of the questions is on that. So so you do that in a very naive way. So okay. So the first question is, after training as SVM, we can discard all examples which are not support vectors and can still classify new examples. Is it true or false?
Looks like true, sir.
Yeah. Does anybody think that this is false?
yes, it is true.
Okay, great. That means you have got some idea about SVMs at least. Okay, so the second question is which you were saying, that suppose you are dealing with a 3-class classification problem and you want to train a SVM model on the data using a 1 versus all method. So 1 versus all method means you will train so suppose you have 3 classes, red, blue and green. So first you will think that red is your positive class and blue or green are your negative classes. So you will train a SVM based on that. Then you will train a SVM based on that green is your positive class and red or green are the negative classes, and red and blue are the negative classes, and finally you will train with blue as a positive class and the other two as the negative class, and like that you will go on. So that is known as a 1 versus all method. So in this case, if you are dealing with a 3-class classification problem, how many times will you train the SVM model?
3 times.
Yeah.
3 times.
Correct.
1, 2, 3. Yeah, 3 times, sir.
Yeah. Okay. And so the final question is, are both the statements about kernel true, which are there in the I have written 2 statements, so are both of them true or one of them is false?
It is a similarity function.
Yeah, the first statement, is it true or false?
It is true.
Okay, and the second statement?
Not really.
Okay.
Not sure, so it is a similarity function. Similarity function.
Yeah. So how do you know the similarity between 2 vectors? How do you know that 2 vectors align with each other? You can think of that geometrically. If you want to think, how will you think of 2 vectors which are completely aligned with each other?
Then they have some intersection.
You are talking about vectors, so you are talking about lines, let's say. So I have 2 lines.
When they are parallel to each other.
When they are parallel to each other, then it will be similar, is it?
And when their direction is same, should be like, so when 2 vectors are having the same direction.
Somewhere when W transpose X plus B is equal to 0. When
No,
the margin is 0.
no, I'm not talking about SVMs now.
Okay.
Yeah, Ravinder was saying something like when 2 vectors, can you continue? You were saying something.
When 2 vectors are like having the same direction, should be similar, right?
Correct. Okay, yeah, that is correct. So how do you decide, how do you know whether 2 vectors are similar, have the same direction? From this lecture, did anywhere you use that fact that 2 vectors, so how do you know whether 2 vectors are the, how do you know the angle between 2 vectors?
Cos theta.
Yeah, so how do you know, what do you do to these 2 vectors to understand whether they are on the same direction? How do you?
We are mapping that, no?
No, don't think about mapping now. I'm talking about 2 vectors which probably have some directions, Now what operation can you do to those two vectors to find out, to get a sense of the angle between them? For example, if they are 90°, what will you do? How will you find out whether two vectors are 90° are perpendicular to each other or not? Okay, I will go back to this particular slide and again ask the same
In
question.
Q I have cos theta we are taking into consideration.
Cos theta is correct. Yeah, so this particular slide, if you see that W transpose X, if you take, you are getting cos theta on the right hand side, correct?
Yes.
So if you are getting, if you are taking getting cos theta on the right hand side, then W transpose X is an operation which gives you a which gives you an indication of the angle between two vectors, correct?
Yes.
So W transpose X, I mean you will require this maybe in other machine learning context also. The W transpose, whenever you want to find a similarity between two vectors, as Ravinder said, you want to find the angle between them, and in order to find the angle between them you need to take the dot product between those two vectors, which is why the dot product is an indication of the similarity of two vectors. Till now it's clear, correct?
Okay.
Right.
Yes. Yes.
So in kernels, this is the definition of the kernel, which is k of xj comma xi phi of xj transpose phi of xi. So now can you answer whether kernel is a similarity function or not? Hello?
Yes. Yes. We
Yeah.
are listening, thinking. We are thinking over it.
Yeah, so let's consider this. Phi of xj is a high dimensional vector
Mhm.
and phi of xi is also a high dimensional vector. If the cos theta between the two of them, or if they are very similar, then kernel will be a high value, correct? Because if cos theta is high, then kernel will be a high value.
Mhm.
If they are perpendicular, phi of xj and phi of xi are perpendicular, then kernel will turn out to be 0.
Okay.
Is this correct, or are there any doubts? Hello? Uh, yeah.
We actually, I'm not sure that whether kernel will become zero or not. Will turn
See,
out
phi
zero.
of xj is a vector, correct?
Huh.
Phi of xi is also a vector.
Yes.
If they are perpendicular to each other, then what will be the value of phi of xj transpose phi of xi? If you are taking two vectors which are perpendicular to each other and taking a dot product of them, what will be the value of the dot product?
W transpose X you told me.
So how do you break up the W transpose X?
W and X into cos theta.
Yeah, so in this case, what is cos theta? If phi
Cos
of
theta 90 degree, na? 90 degree
90
means one. One.
cos of theta 90 degree means 0,
One.
right?
Zero. Huh. Huh.
So kernel becomes 0 in that case.
Okay. Okay.
So kernel,
Multiplying my.
because it is the dot product, so kernel can be considered to be a similarity function. Is this clear?
Yes.
Sir, give this as a homework. We will revisit it.
Yeah, I can't give you homework. So you just remember this, that kernels is a similarity function,
Yeah.
and so you think of whenever you want to find out the similarities between two vectors, you take a dot product, and
Yeah.
effectively kernel is just doing a dot product, and
Right.
because of doing that dot product you can consider kernel to be a similarity function.
It's true.
Okay. Okay, so with that I come to the end of this lecture. It has been a long lecture today, but SVMs were there, so okay. So if you don't have any more questions, I'll close the session.
Thank you so
Yes,
much
sir.
for this wonderful session, Soumya.
Yeah,
I joined late, sir, but I could still understand.
yeah, okay, okay, thank you.
Good, sir. Good. Wonderful, sir. Thank
Mr. Swarma, one small doubt, sir.
Yeah.
Actually, I joined this meeting too late. So would
Okay.
it be possible to upload this session so that I can refer it from the start?
See, I am uploading these sessions to YouTube after the lecture gets over, and that YouTube link should be given to you by the NPTEL people.
Okay.
Okay.
Okay. Thank you.
So from there you would be able to get probably.
Soumya, sir, do you have a channel also?
I have created a channel, I think. Yeah, I have a channel. Yeah.
Oh, wonderful. Oh, wonderful. We'll visit your channel. We'll subscribe it.
Okay. Sure.
All right. Thank you, sir. Thank you so much for your time.
Thank you.
Soumya sir,
Yeah.
these videos will be available all the time, no?
All
Not
that.
only till.
No, all
Okay,
the time
yes.
they should be available. Yes.
Okay, yeah. Thank you.
Yeah.
Thank you.
Yeah.
Thank you.
Okay.
Bye bye.
Yeah. Bye.